Okay, I would like to thank the organizers for this wonderful conference and for giving me the opportunity to talk about the condensed matter problem at the string conference. I'm going to talk about the relationship between fractional quantum Hall effect and duality. And the plan of my talk will be as follows. So I will first review the fractional quantum Hall effect. I will tell you a bit about a standard theory of the fractional quantum Hall effect called the Halperin, Lee, and Reed, or HLR theory that has been the well-accepted theory for a long time. And then I will describe a problem that has been known for about 20 years, but has never found a solution before we start thinking about this problem in a new light. And that leads to a revision of the HLR theory, which now is called the Dirac composite fermion theory. And at the end of the talk, I will talk about experimental consequences, the relationship to field theoretic dualities. So the references, there is a list of references here, and I would like to emphasize these last two papers that put all the, make a very clear that the physics of the quantum Hall effects is tightly connected to the field theoretical dualities. So let us consider the two-dimensional system of electrons moving in a plane in an external magnetic field. We know from 1930 that the spectrum of a particle moving in 2 dimensions in a magnetic field is organized in Landau levels. The Landau levels are discrete because in the classical motion of the electron is periodic. Now, suppose we have a large number of electrons, but the number of electrons is smaller than the degeneracy of the lowest Landau level. Then we have a problem of finding a way to put these electrons on the lowest Landau level so that the energy is minimized. Ignoring the interaction, of course, we cannot solve this problem. So let me define a quantity called the filling fraction, which is a ratio of the number of electrons over the degeneracy of the lowest Landau levels. In this picture, nu would be equal to 2 divided by 6, which is 1/3. The problem can be formulated in, like this. We have a Hamiltonian of n particles in an external magnetic field with some interaction. Let's choose here Coulomb interaction. And we want to find the ground state. In the limit, let's take the theoretical limit, m goes to 0. Then the distance between the Landau levels becomes infinite. That means that we can ignore all the Landau levels beside the lowest one. On the lowest Landau level, since the number of electrons is less than the number of states available, there is an exponential degeneracy of state if there wasn't the interaction that should leave the degeneracy. And so the problem can be formulated as trying to diagonalize the Hamiltonian, which is the lowest Landau level projection of the potential energy between the electrons. There is no small parameter that this fact makes the problem very hard. This is a problem of degenerate perturbation theory with a starting point of an exponentially large number of degenerate states. What we are interested in is how a small perturbation leaves the degeneracy. So it seems that the problem is very hard, but since late 1980s, there is an experimental hint on the direction we should be thinking of in order to solve the problem. And the hint is that there is a gapless state at filling factor of 1/2. If the lowest Landau level is half filled, it seems that the system has non-trivial low energy degrees of freedom, hinting to a very non-trivial physics. And that led in the late 80s, early 90s to the idea of the composite fermions, which I would like to describe. So here, the idea has the origin in the idea of flux attachment. The statistics of a particle does not change if we attach to a particle an even number of flux quanta. So in picture, if we have two fermions, if we exchange them, we get a factor of -1 in the wave function. If now we attach to each of the fermion two magnetic flux quanta, then we get additional Aronoff-Bohm phase when we exchange the two particles, but that phase is 1 in the case of an even number of flux quanta, and so the two particles are still fermions. This picture is formalized into, so let me first explain why that leads to an understanding of the gapless nature of the nu equal 1/2 state. Suppose I have half as many electrons as the number of flux quanta going through the sample. And let me assume that I can represent this electron as another type of particle that we call composite fermions, plus two magnetic flux quanta. Then, if one does a mean field approximation, we see that the new type of particle feels a net zero magnetic field, a net average magnetic field being 0. And that means this particle would form a Landau Fermi liquid, and the excitation, the low energy excitation, will be gapless excitation near the Fermi surface. This leads to the formulation of the HLR field theory. Basically, it is a mathematical rewriting of the idea that has been presented in the previous slide. We have in this theory a field psi, which is a composite fermion, which couples to the external electromagnetic field A and an internal field A0 that has Chern-Simons kinetic terms. And one of the equation of motion that we obtained by differentiating the action with respect to A0 tied to magnetic field B with the density of these fermions. Basically, each fermion leads to a delta functional magnetic field, just as we draw in the previous transparencies. In the mean field approximation, then, the effective magnetic field felt by this psi field is big B minus small b, which is B minus 4 pi times the density of the fermion, and at half filling, the effective magnetic field is equal to 0. This theory implies that we understand the nature of the gapless excitation near nu equal 1/2. And there is actually experimental evidence that this is qualitatively the correct picture. If one, so here is an experiment from 1990s in the newer version of the experiment from 1990s, when one basically look for semi-classical trajectory of these quasi-particles. An electron in a magnetic field moves in circular orbit, but this quasi-particle fields a much smaller magnetic field, and you can tune that magnetic field to give this particle almost a straight orbit. So here, if you tune the filling factor to nu equal 1/2, this particle would shoot in a straight line, and in these, if you go around nu equal 1/2, you can find very large semi-classical orbits of this particle. Two main features of the HLR theories that I want to emphasize here is that first, the number of the composite fermion is equal to the number of electrons. This is by construction, by the philosophy of flux attachment. And tied to that is the Chern-Simons term ADA that leads to the relationship between the magnetic flux and the number of particles. For a long time, it was thought that the HLR theory is the correct theory of the low energy degrees of freedom of the half-field Landau level. Some problems in this theory were known, and some were thought to be serious. But one of the problems that was mostly neglected turned out to be crucial. And that is a problem of particle-hole symmetry. Imagine that we are dealing with a single Landau level. That means the distance in energy to the next Landau level is very large. Then we can define an operation that changes a state in the Hilbert space on the lowest Landau level to another state in the following way. Any state on the lowest Landau level can be represented as the linear combination of state in the occupation number basis. We occupied some orbital and left some state unoccupied. The particle-hole conjugation mapped such a state in a mirror state in which the unoccupied orbital becomes occupied and vice versa. And one can define formally this operation. It's flip the roles of creation and annihilation operator. It's also naturally most conveniently defined as the anti-unitary transformation. The important thing is that it makes map nu into 1 minus nu, which means that a half-field state becomes a half-field state. Or in other words, a half-field Landau level is at the same time a half-empty Landau level. One can define such a transformation. And one can show that this symmetry, this pH conjugation is an exact symmetry of the Hamiltonian if the interaction between particles is pairwise. However, the HLR Lagrangian, which we thought was a low energy description of the dynamics of the half-field Landau level, doesn't have any symmetry that can be identified with the particle-hole symmetry. This problem has been known probably since 1997 at least. It was considered as a hard problem in the hierarchy of problems in quantum Hall physics because it required projection to the lowest Landau level, which makes everything non-local. So a progress is made by sharpening this problem, by considering a quantum Hall effect in a slightly different context, but essentially with the same physics. Consider a two-component massless Dirac fermion. So Dirac fermion in 2 + 1 dimension in a magnetic field. Then we can solve the Dirac equation and obtain the spectrum, the Landau levels, which now would stretch from -infinity to +infinity. The Dirac C becomes negative energy levels. But the main thing is that there is a symmetry E to -E in the spectrum, and there is one exact energy level with 0 energy. Now, if we have 0 chemical potential, that means that we have to decide which state in the 0 level of the Hamiltonian to fill, which one is left empty. And this is now exactly the same fractional quantum Hall problem as we have in the non-relativistic case, except here that we have more symmetry. The relativistic, the symmetry of the spectrum of the Dirac Hamiltonian implies that we have a natural particle Hall symmetry that does not require projection to the lowest Landau level. And so the fractional quantum Hall effect in the for the Dirac fermion, which should exist because it's basically based on the same principle of the degeneracy of the Landau level as the usual fractional quantum Hall effect. It sharpens the problem of particle Hall symmetry. There is now, we don't need to project to the lowest Landau level to have particle Hall symmetry. The half-field Landau level appears at 0 charge density. Now, that implies another problem for the HLR philosophy. The problem is the following. We know that a half-field Landau level from experiment that it is a Fermi liquid. A Fermi liquid with a Fermi with a volume of the Fermi sphere being equal to the number of particles on the lowest Landau level, which is proportional to the magnetic field. On the other hand, we know from many-body physics that there is an exact theorem called the Luttinger theorem, proven for very large classes of Fermi liquids and is believed to be valid also for some non-Fermi liquids, is that the Fermi volume, the volume enclosed by a surface where the fermionic excitation is massless, is equal to the density of a conserved charge. But now in the relativistic problem, the conserved charge density is 0 because we put the chemical potential exactly at going through the 0 energy level. And so if that charge density is the density of the electrons, then it is 0. Then we have a problem with Oettinger theorem. So there is another puzzle that we get by considering fractional quantum Hall effect in the relativistic case. Somehow, this relativistic system puff up a Fermi surface when we turn on a magnetic field. We don't have to turn on any chemical potential to pop up a Fermi surface. A magnetic field itself creates a Fermi surface. So this led, after some try and error, to a proposal of a new, presumably more correct theory of the low energy degrees of freedom of the half-field Landau level. If we have some electron coupled to external electromagnetic fields in a background of a magnetic field with some interaction between the electrons, the low energy theory must have the form of Dirac fermions, two-component Dirac fermion coupled to a dynamical gauge field, which has some Chern-Simons type of, mixing with the external fields. There are two things that distinguishes this theory from the HLR theory. The number of the composite fermion is now not tied to the number of electrons. In fact, these composite fermions now are not directly coupled to the external electromagnetic field. They are electrically neutral. And this theory turned out to be consistent, and there is no Chern-Simons ADA term. It turned out that this theory is consistent with a large number of experimental constraints that I will not mention. So one thing that this type of Lagrangian implements is exchange between the notion of the magnetic field and the notion of density. In terms of the original fermion was the density becomes the magnetic field felt by the composite fermion, and vice versa. The external magnetic field is equal to the density of the electron. So, for example, if you differentiate this action with respect to A0, you find right away that there is a constraint between the density of the composite fermion, this psi, with the magnetic field, which explains why turning on the magnetic field can create a Fermi surface without without any chemical potential. So there is looking backward. The fact that the composite fermion should be a Dirac fermion actually could have been figured out some time ago by just thinking about the physics of the lowest Landau level. The important thing is that the particle-hole conjugation is an anti-unitary transformation, and its square can be either +1 or -1. And the case when it's -1 is non-trivial. On a single Landau level, theta squared is equal to -1 to m -1 divided by 2. M is the number of states on the lowest Landau level. And if m is even, then we can represent that as -1 to some number. And that number is naturally identified with the number of composite fermion. So if that identification requires that the number of composite fermion has to be half of the number of flux quanta and should not be equal to the number of electrons as the HLR theory would tell us. Okay, so the more careful version of this duality was pointed out. It was pointed out that the version of duality that I have just presented to you does not satisfy the matching of anomalies, and Seiberg, Senthil, Wang, and Witten wrote down a more careful version of this duality. If one take this Lagrangian and naively integrate over B, ignoring the fact that the flux of B might be not an integer, we find the naive duality that I have presented to you before. But all what I have told you about the physics of the Fermi surface would remain the same in this theory. So there are some consequences of the Dirac composite fermion theory. First, it satisfies symmetry constraint on transport coefficients, the conductivity thermoelectric constant. It implies a possible existence of a new gap particle-hole symmetric state that may be realizable in quantum Hall system, called the pH Pfaffian state. And it predicts the absence of Friedel oscillation in correlation function of certain symmetric operator. And this has been checked numerically. Let me go through a few of them. One can define the conductivity and the so-called thermoelectric constant by looking at the current in external electric field and gradient of temperature. At exact half-filling, if the particle-hole symmetry is exact, then sigma xy, the whole conductivity, has to be exactly 1/2 of the quantum, and one of the thermoelectric constant has to be 0. So this is a consequence of particle-hole symmetry. Another consequence is that the composite fermion conform a Cooper pairs. If one imagines some possibility of tuning the interaction between the fermion, the simplest pairing does not break particle-hole symmetry. It is this is the pairings that leads to a state that is non-abelian state, which is different from the Pfaffian and the anti-Pfaffian state, which are the two gap states that has been known before in the context of nu equal 5/2, that is half-filled n equal 1 Landau level. And the most non-trivial consequences of the symmetry, and the one that has been checked numerically, is the suppression of Friedel oscillation in correlation of particle-hole symmetric observables. Suppose I have two operators. So I take an operator O, which does not, that map to itself under particle-hole symmetry, and compute the correlation function in momentum space. Usually in condensed matter physics, if we have a Fermi surface, this correlation function has the singularity when the momentum is equal twice the Fermi momentum. And that's because we can create a particle-hole pair when the particle is near one pole on the Fermi surface and the hole is near the opposite pole of the Fermi surface. And the singularity of the phase space explains the singularity of this correlation function, and this is called Friedel oscillation. And it turned out that one can show this, the leading singularity disappear by symmetry reason if the operator mapped to itself under particle-hole symmetry. And these people have simulated the half-field Landau level and found that when we tune the Hamiltonian to be particle-hole symmetric, the Friedel oscillation disappear, which is a very, which cannot, I don't know any other explanation rather than the explanation based on the Dirac nature of the composite fermions. So the fermionic particle vortex duality can be derived from a more elementary fermion boson duality. Taking a fermion boson duality and applying it one more time after taking time reversal, one can derive the duality between the electron theory and the composite fermion theory. The elementary boson fermion duality can be thought of as the small n equal 1, basically version of the duality, one duality between Chern-Simons theory that has been tested at large n. But this is a really small n case. Using these dualities, new dualities can be obtained. In one example that is also interesting is NF equal 2 QED in 3 dimensions can be shown to be self-dual. So the the elementary duality looks like a map between a theory of a single fermion, two-component fermion with the, thank you, with the scalar with the Chern-Simons interaction. So let me go to the conclusion. The Dirac composite fermion theory solved a 20-year-old problem of particle-hole symmetry of the half-field Landau level. It gives a new understanding of the low-energy dynamics of the half-field Landau level, and it gives distinct prediction, some of which has been numerically checked. And what is interesting for me, at least, is that it is one can think about this quantum Hall system as experimentally accessible windows to some small part of field theoretic duality between 2 + 1 dimensional theories. Thank you very much.
Are there questions?
Do I understand correctly that you're saying that the theory of Halperin et al. Is dual to the theory you have? Is that the statement?
There is a work by Halperin, Stern, Wang, where they computed 2 physical quantities, and they see that they satisfied, for these 2 quantities, particle-hole symmetry is satisfied, and they reproduce the result of the Dirac composite fermion theory. I believe this is coincidence. There are, if one take generic correlation function, like correlation function of 2 current, doing the calculation, I did the calculation, and the HLR theory gives results that are not particle-hole symmetric and distinct from the Dirac theory in most of the cases. These 2 cases are somehow these 2 quantities are really special.
Oh, I see. So you have a theory which is different from their theory, and I didn't understand the role of duality. So you had this theory. Why is duality playing a role?
Well, it does provide at least philosophy that would replace the philosophy of flux attachment. So the old picture of flux attachment is very attractive because it's really intuitive. You just take the electron and transform it somehow into a composite fermion. And
to me, that sounds like a phenomenological rule, but it sounds more natural from field theory to say that you write down Lagrangians that are natural with Chern-Simons terms and so on. So I'm not sure why we need to invoke flux attachment. It sounds like it's a rule that gives the wrong answers for this problem.
I'm sorry, I don't understand your question. So you ask why I need the Dirac, I need the duality.
Yeah, why do you need flux attachment? Why do you need this picture? Why don't you just simply write down Lagrangians with Chern-Simons terms, as you are doing?
Well, that's basically what I did. That is, write down a theory that satisfies the symmetry. In particular, this particle-hole symmetry give a key that give a hint to how such a theory can be written down. For example, a small ADA would not exhibit any discrete symmetry that can be matched to theory. The interesting thing, I think, is that we know that this is, and we know from experiment, basically, that this is a correct theory when the magnetic field is non-zero. And the interesting thing is that whether the duality between these 2 theories can be valid also at zero magnetic field. And this is, I think, is more open question. And it is basically the statement of duality. So duality is not needed per se for fractional quantum Hall effect, but I think at least from my point of view, it's the other way. Going from quantum Hall effect, one might get the hint of the duality in such a way. Yeah.
In the second line,
Yeah,
the last term doesn't seem to be correctly quantized.
the last term doesn't seem to be,
Correctly quantized.
it's not correctly quantized. Yeah, so the idea to correct this, you have to introduce an extra field called B. So these two theories have exactly the same anomalies now. But if I integrate out the B gauge field naively, the setting B to be the saddle point, then I would get this theory that I talk about. So if I'm just interested in local physics, for example, computing response transport, then this is a good enough theory.
So can you...
Before I have this one.
Yeah,
Yeah,
this one.
that has the same problem, and it needs to be slightly fixed in a similar way to what you showed for your theory.
It has the same problem.
It has the same problem. It has an improperly quantized Chern-Simons term, as you've written on the slide there, and it needs to be slightly corrected in a similar way to what you said for your theory.
Yeah, but we know how to correct it. Thank you.
I know that, but
Yeah.
I think that was perhaps with the responsive to the question.
Yeah.
There seems to be no more questions, so I suggest that we thank Damson again.
Thank you.